All right. Well, welcome everyone. My name is Brian Staley. I am President and CEO of the Environmental Research and Education Foundation. Thank you for joining us today for today's science session entitled Elevated Temperatures and Landfill Fires, What's the Difference? This is a topic I'm particularly excited about. For many of you who are familiar with EREF, you know, as a research foundation, we fund research around a variety of different challenges and topics across the waste field. And this particular topic is one that EREF has invested millions of dollars in trying to evaluate what the difference is between elevated temperatures and landfill fires. And so that's what we'll be talking about today is how are landfill fires different than elevated temperatures? How do they behave differently in landfills? And what things could potentially be done about that? So let's go to the next slide. Before we begin, there's a couple of housekeeping items. You can submit questions anytime throughout the presentation using the Q&A icon at the bottom of your screen. For those of you who are joining us live, tomorrow you will receive an email from Zoom with a link to both the presentation and a survey where you will also be allowed to download a certificate of attendance. Let's move to the next slide. So all participants are muted, and feel free to submit your questions anytime. We'll be looking at that, and then when we get to the Q&A session, we'll be looking to address as many of those as possible. One thing to note that as we move through this, the run of show we'll have a presentation from our panelists via slides. We'll cover elevated temperature landfills first, go to fires, and then after that, we'll go to a question and answer session. Our objective is to try to have a good portion of the time, ideally about half the time, dedicated to really having a conversation around ETLFs and around landfill fires. Our panelists have agreed to continue the conversation beyond the hour we have allotted, so we may go long. And for those of you who maintain interest in the presentation after the hour, feel free to stick around and we'll keep talking. And certainly if you do have to run, as we noted earlier, you will be able to get a copy of the recording. So now I'm pleased to present our panelist for today. Mort Barlaz is a distinguished university professor emeritus in the Department of Civil Construction and Environmental Engineering at North Carolina State University. He's been involved in research on various aspects of solid waste since 1983, including biological refuse decomposition, methane production, the fate of hazardous waste in landfills, policies for the long-term management of landfills, and factors contributing to heat generation and accumulation in landfills. Dr. Craig Benson is an international authority on landfills and waste containment. His expertise includes municipal solid waste, hazardous waste, cold combustion residuals, mining and mineral processing wastes, and low-level radioactive waste. Dr. Benson served as Dean of Engineering at the University of Virginia and in various leadership roles at the University of Wisconsin-Madison before entering emeritus status. Benson is a professional engineer, past president of the ASCE Geo Institute, and member of the National Academy of Engineering. And we have Bill Meyer, who's been involved in the landfill gas industry for 44 years, engaging in a broad range of activities, including well field operations and maintenance, gas collection and control system design and construction, landfill gas to energy plant design and operations, and landfill gas-related environmental compliance. His comprehensive experiences in technical, operational, and environmental aspects of landfill gas management, and he currently serves as Senior Director of Special Operations Support at WM. So with this esteemed group of speakers, I'll turn it over to them to begin the presentation.
Thanks, Brian, and good afternoon. Appreciate your afternoon or morning, depending on your time zone, I suppose. As Brian indicated, I'm going to speak first to elevated temperature landfills, and Craig and I will rotate a little bit, and then we'll transition over to fires. What I hope to cover is a little discussion of what is an ETLF or elevated temperature landfill, and that will include definition, causes, characteristics. We'll talk about indicators and how to recognize an ETLF and best management practices. As Brian indicated, we're hoping for a short overview today to allow lots of times for questions. The EREF website listed here is an excellent resource for articles and recordings of more thorough webinars that were given over the past year or two. Next slide, please. So to begin, what is an elevated temperature landfill, or ETLF? And the working definition that we use is a landfill experiencing persistent elevated temperatures over a broad area. What is persistent? It means way more than, well, gee, we had one hot well this month. So wellhead temperatures, once they're getting above 150 to 158 F, would certainly be cause for concern. As I'll stress later, we're not going to ever characterize an ETLF based on one indicator alone. What an ETLF is not is a landfill with one or a few hot wells. A recent estimate showed that about a third of all U.S. landfills have at least one hot well. So there are a limited number of these sites in the U.S. Many have exhibited temperatures above 100 C or 212 F, and obviously they need a lot of monitoring and management. Next slide. So let's talk a little bit about characteristics, starting with wellhead temperatures, where if we say typical is 40 to 55 C or 104 to 131 F, but even up to about 149 F, we can still be getting good methane generation. Once we get above that, we're starting to touch an area where methane generation is inhibited, and that is certainly an indicator of an elevated temperature situation. I want to stress that there's literature that shows that the solids associated with hot gas are hotter by as much as 15 or 20 degrees C. So that if in fact we're seeing wells at 150 degrees F, we might have solids at 170, 180 degrees F. And so certainly when you're up at the upper end of these typical ranges, it is appropriate to probe more. That might mean installing probes or borings and looking at solids temperatures. And as noted on the next bullet, we've seen temperatures above 300 degrees Fahrenheit. And in addition to gas, obviously, if you see elevated temperatures in gas well liquids or leachate, that too is an indicator. The slide, excuse me, the figures on the right just show profiles of temperature versus depth, and you see a normal temperature zone on the left and an elevated temperature zone on the right, and characteristically this belly curve with the warmest temperatures near the bottom or below halfway down, and obviously that's going to be site specific. Next slide. In terms of physical attributes, rapid settlement or crack development in interim cover soil or final cover, steam release from gas wells or waste borings. When the temperature gets hot, a lot of times the gas and leachate collection systems, the piping is rated, say, for under 140, 150 degrees Fahrenheit. So sometimes when we get heat, we see softening or bending or pinching in this infrastructure, which is another indicator that things subsurface are warm or hot. While not an indicator per se, ETLFs seem to be associated with perch leachate or large accumulations of water in the waste mass. Next slide. So moving to indicators of gas composition, changes in gas composition. So we talk a lot about the methane to carbon dioxide ratio. So decreased methane, increased CO2 are typical. We may see an increase in carbon monoxide as well as an increase in hydrogen. I write interpret carefully because we get biological production of CO, carbon monoxide. When the system is working well, that carbon monoxide is consumed by the methanogenic consortia that's converting MSW to methane. Similarly, hydrogen is produced during the acid phase of decomposition. So a small accumulation, for example, if I had a truckload of rotten food waste and I buried it and I put a gas well right in, I would expect to see hydrogen because that waste is going to be stuck in the acid phase. And on the other hand, if the system is hot, the bacteria or the microorganisms that consume the hydrogen are inhibited, and then hydrogen accumulates because of temperature. Hydrogen moves quickly. In a healthy
Mhm.
system, it's consumed very quickly. Um, but let's come back to this idea of a decreased methane to CO2 ratio. If you look at the plot on the bottom here, you see over a period of 4 years, the methane to CO2 ratio decreasing. But if you look at the parallel period of 4 years on the plot above, that temperature stayed pretty stable for many years while the methane to CO2 ratio was decreasing. And we'd always talked about, well, there's this concurrent drop in ratio with an increase in temperature, but actually that ratio dropped first. And I've seen this at other landfills as well. And this we will emphasize throughout this presentation, plot your data, look at trends. If you see a trend like this and the temperature's normal, don't pat yourself on the back and walk away. You have to dig further. Um, and then that last bullet just pointing out decreased methane means the gas may not burn completely, which may result in the discharge of odorous gas. Next slide. Um, this is just to kind of pick up on this notion of methane to CO2 ratio or gas composition. On the right, I've sketched a hypothetical waste column. And let's assume we've got a well, it's slotted for 2/3 of the length, and there's a lens in that waste column that's hot. And that lens that's hot is going to be biologically inhibited. We're going to get less gas. So if I've got 40 CFM above and below that hot lens, making normal gas 50/50 or 60/40 methane CO2, and then I've got 5 CFM, even if the methane content is 0, I probably won't see it in a ratio based on what's coming out the top of that well. And so, again, this is why I'll keep stressing there's no one perfect indicator other than temperature. But by the time you see temperature, you're behind. Next slide, please. There's been a lot of discussion recently about DMS or dimethyl sulfide. It's common in ETLFs and a lagging indicator, and I stress lagging indicator. But I've seen all kinds of, well, is this our leading indicator? Should we look for DMS everywhere? No. There's kind of a simple explanation for why we see DMS in landfills. First of all, it's present in many of the wastes that are disposed of in landfills, food waste, yard waste, biosolids. Second, its boiling point is 99 degrees Fahrenheit. Water boils at 212. In other words, a lot of it's in the gas phase. And third, under healthy conditions in an anaerobic ecosystem, the DMS is converted to methane, methyl mercaptan, and H2S when the methanogenic consortia is healthy. When methanogenesis is inhibited, DMS accumulates. So that's why we're seeing elevated DMS at some ETLFs. The plot on the right is data from a site where you see exactly what we'd predict. Warmer temperature and more DMS because we're increasing volatilization. Next slide. So I'm actually going to turn it over to Craig here.
Thanks, Mort. I'm going to dovetail on some of your remarks. One of the things that is really important is that we not only collect data, but we think about what it means. We look at trends, we try to interpret what the data mean in terms of the health of the waste within the landfill. Historically, we would often see carbon monoxide and think, oh, it must be a fire. And we would automatically go into a fire suppression mode. But when we see carbon monoxide, we need to look at that and say, what else do we see with it? And one of the common attributes at ETLFs is both the presence of carbon monoxide and hydrogen in the gas phase for exactly the reasons Mort talked about. And I just show here a typical graph that I have from one of the sites I'm involved with right now, a very clear trend between carbon monoxide and hydrogen because that microbial pathway has been disrupted, as Mort very eloquently described. So when we see carbon monoxide, we should ask ourselves, okay, what else are we seeing? Does it make sense? Does it not make sense? And then take action that's appropriate. And that type of thinking is critically important for analyzing any of these sites. Collect data, analyze the data, interpret what it means, and then decide a course of action. One of the other things that we think about in terms of indicators and characteristics is we often see more leachate at ETLFs. And whether how significant that is a bit of a debate. But we do know that when we take a waste mass that's moist and we heat it up, it will soften, and the pore spaces in that waste mass will hold less water. The surface tension of water also diminishes as the temperature increases. Those both contribute to water release from the waste and draining into the leachate collection system. So we'll often see a greater volume of leachate being produced. But at the same time, too, we're often, because many of our sites are watered in, we'll be having dual phase extraction wells in there, and we'll be pumping those, and that'll also be contributing to leachate volumes as well. So we need to think about where the different leachate contributions are coming from. That principle I talked about of softening the waste is shown here in these photographs on the right. These are from some experiments that Nicole Berger did at University of South Carolina. But you take this moist organic matter and then heat it under an oxygen-free environment, and this is what you end up with. You end up with something that's with lots of water. No visible water here. It looks moist, but no visible water. Lots of water here, and lots of stuff dissolved in the water as well. So not only do we have the presence of leachate, we also have more constituents in the leachate, which is common in ETLFs. Characteristics and indicators following from that. Because the leachate is changing, we'll see attributes of the leachate changing along with the alterations in the waste mass. So, for example, BOD and COD will often increase dramatically as temperatures pick up, and notably the BOD to COD ratio, and this is important, it will also climb as well. And I find when things are really get hot, that ratio would be right around 1 often, the BOD to COD ratio. And the BOD and COD levels or concentrations will be higher than you've ever seen before. One of the complications with BOD or COD in the leachate is it often isn't a leading indicator, but somewhat of a lagging indicator because of a similar analog from what Mort talked about with gas wells. Leachate, by the time it reaches through the leachate collection system, has passed through a number of different layers of waste, some which may be very hot, some which may be in a much more normal condition. Other things that we see as well, we'll see phenols, we'll see acetone, we'll also see lower pH because the methanogenic process has been disrupted as well. An important attribute is thinking about where we're getting the leachate from too. If we sample liquid from gas wells, it will tend to be more concentrated from what we'll see in the leachate collection system because we're sampling it essentially right out of that pore space. Things that we see when we look at leachate from ETLFs, organics concentrations tend to be much higher than what we would see in typical MSW leachate. And I just show that here with a graph on the right. These box plots are ranges of concentration observed at ETLFs, and the numbers below them are median values typical of MSW leachate from a report by Nate Klett et al. In 2009. And you can see typical organics concentrations in ETLF leachates are at factor of 10 and sometimes a factor of 100 higher because we have decomposition of the organic matter under elevated temperatures and anaerobic conditions. That's essentially a pyrolysis reaction, creating decomposition products that end up in the leachate. As I indicated, but leachate composition can be a trailing indicator because of the commingling of different layers. So we do need to pay attention to that. How do ETLF leachates differ from those that we see at sites with combustion? They are different. There's a limited amount of data on this, but from what we've been able to gather, we'll see that ETLF leachates, for example, the COD will be much higher, as I indicated earlier. It'll be a factor of 10 higher than a conventional, and also a factor of 10 or higher from what we'd see in a combustion setting. So if we have a fire, our leachate concentrations are not going to have the same COD that we would see from a fire event compared to an ETLF. ETLF COD will be way high, and the pH will be considerably lower because of disruption in the methogenic activity within the waste mass. Finally, just some characteristics and indicators, things that we should be looking at. As Mort indicated, decreasing methane to carbon dioxide ratio. That's truly a leading indicator. We get in a mode of monitoring gas wells, writing data in a table, putting it in a report, sending it into the agency. What we need to be doing is collecting that data, looking at it this month. How did it compare to last month? How does it compare over the last year? Do we see trends in that data that look healthy or problematic? And if they're problematic, then we need to take action earlier on as we can. Look for other things like carbon monoxide and also hydrogen and other balanced gases. And look for elevated organics or low pH in our gas well liquids as well. So they're all indicators of potential problems before that we can see early on. And then, as Mort mentioned, the unusual reduced sulfur compounds, the DMS is a good indicator for that. If we do start seeing that, we want to be thinking about what actions do we need to take. Lagging indicators, elevated gas and liquid temperatures. By the time the gas temperatures start to drop, we've got problems. Excuse me, when the gas temperatures increase, we've got problems. And when liquid temperatures are high, we're too far gone. Temperatures are high. That means we've got a condition that we've got to deal with immediately. Unusual settlement and cracking and deteriorating leachate quality over the site-wide area or contributing area. These are all lagging indicators. Importantly, as Mort talked about, it's not one thing, it's multiple indicators. Look at the data, compare the different data sets you're getting. Does this make sense in an integrated manner? Am I seeing all the telltale signs, or is it just one? And if it's just one telltale sign, then we need to think about, well, maybe it's not that important. Maybe it is. We'll continue to collect data and analyze it. But looking for trends over time as well is particularly important. Most ETLFs develop over years. In some cases, I think 10 to 15 years before they truly become manifested and become problematic. Mort, I'm passing back to you.
Yeah. So what's the cause? And skipping to the third bullet, we don't always know, but let's give a longer answer. There's been a lot of research, a lot of it supported by EREF. We've shown that the hydration and carbonation of ash can contribute considerable heat. We've also shown that every ash is different. So trying to make a rule of thumb based on one ash won't work. We've all heard about aluminum dross. Aluminum oxidation or corrosion gives off a lot of heat. And then I'm going to stress this notion of heat transfer. Once it's hot, that heat is going to move even if waste is not, quote unquote, reacting. If I've got hot ash next to a typical MSW, some of that heat is going to move from the ash to the MSW. But the fact is, we're not always sure why a site got hot. And after the fact, focus has to be on management and control. We can't, obviously, we want to know why. To the extent that there's air intrusion, which isn't the ETLF, but causing heat, we have to deal with that. But we don't always know the cause. There's lots of speculation. There are sites where reactive waste are the explanation, but there's others where we just don't know. Next slide, please. And then finally, I want to, excuse me, just point out the issue of surface area. Heat accumulation tends to be worse at sites with a low surface area to volume ratio because there's a smaller area for heat release. On the bottom, we've done a lot of modeling to look at landfill temperatures, and we're simply showing that for the same surface area, if I've got a site that's about 40 meters, that's the dotted line, versus 80 meters, the solid line, over time, the 80-meter site is hotter. And that's simply because I've got less heat flux or less heat release to the surface. The
Mhm.
plot on the right is just the volume fraction above about 105 degrees, and it tells the same story. Next slide.
Okay, I'm
Back
going
to
to
you, Craig.
take this one. Yep. Yeah. A lot of ETLFs really boil down to heat transfer problems. I think that Mort just alluded to that with the modeling graphs he showed. We, in a healthy landfill, the heat that's generated tends to be dissipated into the environment. But when we have excess sources of heat, we just can't dissipate them. We don't necessarily have a reaction that's propagating or moving around through the facility. We have an area that's warm or hot, and it will then move, the heat will move away from that just due to the thermodynamics of heat transfer. The heat accumulates because the system can't release heat as rapidly as it's being generated. It's actually a very, very simple problem in many ways. Solving it, not necessarily as simple. But if you think about it, if we have some heat developing down deep within the landfill, that's going to cause uh, conditions within the waste mass to heat up at depth. We talked about a belly curve earlier, where we end up with hot leachate. This area near the base will tend to decompose more rapidly or deteriorate. This tends to become a lot less permeable over time. I've sampled waste from this section of the landfill, which is deep below perched liquid, which has been very hot, and I get hydraulic conductivity sometimes in the middle 10 to the minus 8 centimeters per second, like it's a clay liner type of material. That moving water out of that waste mass can be difficult, and moving heat out of that waste mass can be difficult as well. We think about our pathways for heat removal. We have dissipation from to the earth. That's a slow process, a very slow process. We have release to the atmosphere. That's not as slow as to the Earth, but it still is a slow process because we have very long distances from the heat generation to the boundaries. But we do get some convection of air along the surface, which helps us. Now, if we're in a quarry landfill, that's not going to work as well as if we're in a more conventional landfill above grade. But we'll see that removing heat by these diffusion pathways is not particularly efficient. What we really need to think about is how do we pull heat out through our fluids within the landfill. Our leachate collection systems I show here, just a conventional side slope riser, but we're probably going to have dual phase extraction wells throughout the waste mass, pulling that liquid out, pulling the gas out, and pulling the heat along with it as well. ETLFs largely are landfills that have a source of heat and a heat transfer challenge. And if we can accelerate the heat transfer, we'll help address the problem. And I think I'm passing it back to you, Mort.
Right. So to try to summarize, landfills are complicated, lots of confounding factors, hard to simulate a landfill in a highly controlled environment. I do make the general observation that if we think beyond landfills and look at most industrial accidents or upsets, if you will, it's typically because multiple things went wrong at the same time. And so for a landfill, that could be reactive waste plus liquid accumulation plus heat release. Again, hypothetical, but just pointing out it's often not that somebody did one thing that didn't work. Next slide. I want to just wrap up by pointing out some issues related to heat migration. I said earlier, heat moves from hot to cold. But I also want us to think about condensation. If I've got a hot area of a landfill, let's call that box A, with saturated water vapor, and box A is hotter than box B, then steam from box A is going to move in the direction of box B. When that steam hits the cooler waste in box B, that steam is going to condense. When it condenses, it releases heat. It's the opposite of evaporating water. It releases heat. So when we see temperatures moving from hot areas to typical areas, it doesn't mean that the quote unquote reaction is spreading. It means that heat is migrating. The reaction may or may not be spreading. And I think we frankly have to face the fact that that's going to happen and plan and design and manage accordingly. This notion that we're going to draw a line in the sand and a barrier and contain all the heat, in the absence of an air brake, that's probably not going to be what happens. Next slide. So lessons learned. Maintain aggressive gas collection. High operating variances are likely going to be required and are essential. Look at trends. We've talked about looking at trends over time. Keep liquids draining. Do not allow liquid accumulation. If you get a really, really wet month and there's no leachate generation increase, check out why. Should there be? Go back in your records, see if there was 2 years ago. That might be an indicator that liquids are not draining. Obviously, install covers to enhance gas collection and reduce infiltration. And think carefully about the special waste that you accept. Special waste protocols are essential. We've learned the hard way from aluminum dross that too much of the wrong waste at the wrong place can be very, very problematic. Next slide. So in summary, we can manage ETLFs, but we can't necessarily stop the reaction. We have to focus on prevention and on management, and every site is unique. I'm very reluctant to give one-size-fits-all approaches that you're going to do all this at every site all the time because sites are so unique. And with that, let me turn it over to Bill.
Yeah, good afternoon or good morning, everyone. And thank you, Mort, and thank you, Craig, for summarizing ETLFs. I have a few slides here that I'm going to transition over to the landfill fires. And really, this is, as the title of our presentation really itemizes, really I'm going to highlight the differences of what we see between an ETLF situation and a landfill fire. There are situations, there are in the literature and everything, and just common conversations within the solid waste industry, it's very easy to have the transfer of information or the assumptions of landfill fires are ETLF situations, and they're quite distinct. And so I hope the goal of my presentation here is going to give you the ability to identify what a fire is versus an ETLF situation, and also give you some rules of the road, some high-level ideas of how to manage them, how to recognize them, and then also really most critical is how you bring your gas system back online after mitigating a fire. And so that's the hope of my the presentation today. Next slide, please, Craig. Yeah, let's kind of discuss here of how to recognize a subsurface fire situation. In that first sentence, there's quite a bit going on in that first sentence, and let me kind of piecemeal it here a little bit. When we talk about most subsurface landfill fires, really what we're identifying there, what I'm trying to identify there is make the distinction between a subsurface fire that may have been caused by a hot load, for example, lithium batteries or some type of chemical or some type of reactive material that comes into a landfill that initiates the fire situation. Those are distinct events. Separate to what I'm going to focus on is really landfill fires that are associated with the operation of a landfill gas collection system. So I just really want to kind of provide that distinction. Now, those subsurface fires that may be caused by some other reaction could definitely impair or damage the gas collection system, no doubt. But really, the cause of them the initiation of them are completely separate events. And so really kind of walking through that sentence here, further on, we cause when oxygen from the atmosphere is induced into the waste mass. And this is really a critical aspect of the conversation. You know, in Craig and Mort's presentation, not once did you hear the mention of oxygen in their conversation, because oxygen is really, in an ETLF situation, is not a parameter that we focus on, because an ETLF situation is typically deep within the landfill, whereas a landfill fire is near the surface, where oxygen is really a key component of propagating that flame, that fire, at the near surface of the landfills. Now, kind of continuing on through that sentence there, where the oxygen is introduced into the waste mass. If you remember your high school chemistry, you have the triangle, the heat, for a fire. You need oxygen, you need a fuel source, and you also need heat, enough heat to generate a sustained flame. And that's really what we're talking about here, is that oxygen is basically come into the landfill due to a overpull situation, damage of a gas collection system, impaired device, cover, all those type of things that are mentioned in that summary below. And they influence then that local event, then heats up to a point where you have basically the heat is sufficient to sustain the flame and to use the fuel source there for a sustained heating event. And that's really what we're kind of focused on right now. As you can see that, you know, we talked about the over extraction of a gas extraction well, nearby erosion rail, and damage to the gas collection system. And those are all systems, all events that are near surface, that are within the top 50 foot of the waste mass. And they're also typically, I think most people on the call here who have familiarity with landfill fires, you know, there's a tendency to have a perimeter gas collection device to be more prone to having a landfill fire than one that's in the interior of the waste mass, strictly because it's more has more accessibility to oxygen near the slope. The perforations are near the slope, and very easy to overpull on a perimeter gas collection system. Next slide, please, Craig. So what are the characteristics? Mort and Craig spent a number of slides there talking about the characteristics of an ET event. And, you know, we have a little bit of cross similarity with an ET event, but there are distinct differences. Subsurface landfill fires are very short. They've basically been propagated through a relatively short period of time and a localized settlement. Mort mentioned that, you know, with an ETLF situation, it could basically propagate over a number of years and then finally come to visibility through the data, through the management of the data, because of perhaps we just didn't have collection devices in that area. Whereas with a fire, it's really evident. It's near the surface. Typically, you know, you'll always see smoke. You'll always see, you know, if it's near a gas collector, you'll see the gas collector being pinched, melted, leaned over, all those type of things that are very physically, you know, that you can see. Now, that's not to say that all fires are going to be located right next to a gas collection device. I've been on some fires where the source of that oxygen into the waste mass was completely on the other side of the hill, well over 500 feet away. And that's because that fire is searching for that oxygen. It's trying to find that vein within the waste mass to bring that oxygen into the waste mass and to, you know, potentially create a fire situation. Both Craig and Mort really stressed the importance of data. And this is similar to a subsurface landfill fire event. And when you're looking at the data, the abnormal increase in landfill gas temperatures. And, you know, NSPS is right now, the operating temperature is 145 degrees. But that's not to say that every well at 145 degrees has a landfill fire. What we're saying here is that there's any rapid increase in wellhead temperatures. You know, typically we look at something like on the order of a 15 or 20 degree increase in wellhead temperatures. That's just go from one monitoring event to the other. It's just, just unexpected. And that really causes you to kind of look into the data and see really, is it because my vacuum changed on my wellhead? Is it because of, inaccuracy of the instrumentation? Whatever, but that's really causes you to go back and look at that temperature wellhead on that wellhead temperature to verify that temperature. We talked about carbon monoxide. And once again, carbon monoxide is a characteristic in ETLF situation. It's the same thing here with a subsurface landfill fire. It's really the result here of an incomplete combustion event. We typically look at 1,000 ppm as a threshold for a fire event. We've seen situations where even 500 ppm, along with wellhead temperatures, along with the degradation of the methane concentration, is an indicator of fire also. So there's really no, definitive, it's not, we're not hanging our hat on 1,000 ppm. Similar to ETLF, you have to take all this data together to make a judgment case of what's going on, if there's any abnormal events going on with your gas collection system. And lastly here, smoke. With all the landfill fires that I've been on, that I've been associated with and looking into, smoke is always a common characteristic. You have combustion, you have smoke, and that's a common theme with any type of fire. Next slide, please, Craig. Yeah, this is a really good slide here. This is a lot of information here on this one slide here, and this is really kind of illustrating the importance of oxygen. As we mentioned, oxygen is a requirement for any type of landfill fire, but it's also a key parameter of how we judge the health of our gas collection systems. Now, these concentrations here that are illustrated are strictly the wellhead concentration. This is not reflective of what's going on within the well, let's say 100 feet down into that well casing. This is what's measured at the wellhead. And as we know, as operators of gas collection systems, that there is a lot of variation on that measurement. That could be impacted, the wellhead oxygen concentration could be impacted due to the integrity of the well casing. It could be impacted due to, let's say, a pneumatic pump operation. It could be impacted by, a boot on a liner. All those type of things are impactful to that measurement of that oxygen concentration at the wellhead. But it's not a true indicator if I have 10% oxygen at the wellhead, for example, then I'm automatically going to have a fire. No, it's really, once again, you have to take all this information in and to make observations on both the chemical characteristics of the landfill gas, along with the physical, when you're out there looking at the wellhead, looking at your gas collection system, if there's any localized settlement, any degradation of the wellhead structure itself, that are indicators of a subsurface fire. And lastly, on the bottom right-hand corner of the slide I think is really important when you're looking at this, is really looking at the wellhead temperatures. Through all this data that's for the past 6 months here of over 270 sites, there was 240,000 data points that I looked at. And, these are the average wellhead temperatures. So when you look at that wellhead, that oxygen range of 5 to 21%, the average wellhead temperature is 85 degrees. Really, by looking at that, sure, there's no really obvious indication of a subsurface fire event just because we're pulling in 10 or 15% oxygen. Of course, it's detrimental to the gas collection system. It has to be investigated to maintain a gas quality if you have an RNG plant, power plant facility, or just environmental compliance at your facilities. But once again, from this data set, there's no direct correlation that if just because I got 5 or 10 or 15% oxygen in at my wellhead at my measurement that I'm automatically going to have a fire. So you can see that through that gradation there with wellhead temperatures, from 0 to 9.9% oxygen, the wellhead temperature of that data set was roughly 120 degrees, still well below the NSPS threshold of 145 degrees. Next slide, please, Craig. This is a slide that I thought would be beneficial to kind of try to summarize the differences here that we've discussed here on these series of slides between an ETLF situation and a subsurface fire situation. Kind of walking down this table here, the depth of the hot zone. Once again, the elevated ETLF situation is deep within the waste mass. Mort showed that belly curve that's indicative of a deeper landfill, deeper heat signature within the waste mass. Whereas subsurface fire is typically near the surface, typically within 50 feet of ground surface. Once again, because it's very easy to have that oxygen influence into that waste mass due to improper cover, erosion rails, broken collector, broken GCCS device, all those type of things that are easy pathways for oxygen to get into the waste mass. A little bit on physical characteristics. I think we're all familiar with the smoke, the charcoal-like smell. It smells like your barbecue that you have in your backyard because it's kind of that incomplete combustion type of a scenario of a fire. Damage to the gas collector, the wellhead, noticeable change in ground contour. And that's really important when you're trying to put out a subsurface fire because there may be a bridging effect on that ground cover that when you bring a small piece of heavy equipment on it, or you're walking over that area, if there's a bridging effect, it's very easy for that material to cave in and cause a significant safety issue. I've been in some situations where that ground is basically due to the bridging of material has dropped well over 5 feet once you kind of got near it and everything like that. So it's really a safety aspect on all this, either an ETLF situation or a fire situation is really critical to maintain your safety per your company guidance. On the ETLF situation, yes, smoke / steam may be present. We talked about the steam plume. Mort talked about that 212 steam plume. There's maybe smoke, there may be steamers come out of cracks that on the surface due to the pressure that's built up within the waste mass. Potential increase in wellhead static pressure. And why is that? That's simply because perhaps your gas collection system does not have sufficient system vacuum available to pull off that excessive pressure that's within the waste mass at your wellhead. And as a result, your pressures at your wellhead will typically increase. And chemical-like smell, and that's really very unique. If anyone's been around an ETLF situation, is really the first thing that everyone talks about is the distinct smell. It's a very chemical, very acid-like smell. It's very, once you have that smell, once you have that drip of that condensate on your clothing, it'll never come off. And you just kind of have to throw away that clothes because it'll just never come off. But anyone who's around an ET situation is very familiar with that distinct smell. A little bit on the landfill gas side, we talked about carbon monoxide concentrations. It's really elevated situation with a subsurface fire. In fact, when you're going quite often as landfill operators, we know when you're going back to the agency for HOVs, for kind of documenting the fire, really the common thing that we do is supply Draeger tube readings for carbon monoxide. And that's really a key component that we look at. And once again, the key with with Draeger tubes is that you want to make sure that you're taking that sample per the vendor specifications. Some of these Draeger tubes are very temperature sensitive. And so you got to make sure that you're taking those samples per the vendor specifications. As both Morton and Craig really emphasized, really the looking at data. Data is key for both the looking at subsurface fire events or an ET situation. You're looking at that trending that data. Now, of course, with a fire, it may be more short term. You may be only looking at 6 months worth of data, whereas with an ET situation, you may be looking at multiple years worth of data to try to diagnose what is going on. What's the long-term objective? How do I remediate the situation? So it's really important that we really focus on data. With a fire situation, you're looking at the rapid decrease in methane concentrations. And as Mort indicated, a leading indicator for an ET situation is that reduction in that carbon dioxide or methane to carbon dioxide ratio. Typically, it seems like the industry is really focused on when that methane CO2 ratio drops below 1 or drops below 0.9, that's when it's really need to have a refocused effort of looking at an ET situation. And really the speed of reaction, once again, this is very site-specific, very anecdotal, but generally speaking, that a subsurface fire, it's relatively quickly. Everything may be great one day. You may come in Monday the following week, and you may have a fire situation on your hand that you may have to look at. So sometimes it happens overnight. Sometimes it happens monthly, or it takes multiple months to propagate. Whereas with an ET situation, it may take years for it to actually propagate to a point where you actually have data enough to indicate a situation. And really, the last bullet here is really important, that both your landfill gas operators, your technicians, your consultants, whoever's operating your gas collection system has firm knowledge, firm understanding of how to recognize these parameters if they're trying to diagnose a subsurface fire or an ET event. Next slide, please, Craig. Okay, so how do we mitigate? We've kind of talked about trying to what we look at to identify a subsurface fire event. We've looked at some of the causes. Okay, so now we have a fire. So what do we do now? Typically it's not a 911 situation. Really, the key conversation here is really you want to mitigate the oxygen. Oxygen is the key to fires, and so as a result, when you pull that, remember that we got our three legs on our chair. We got oxygen, you got a fuel source, and you got heat. So oxygen is the easiest one to pull to mitigate, to break that fire, that triangle. And so we really want to focus on oxygen. We want to focus on the mitigation of oxygen into that area, that impacted area. So how do we do that? We place a low permeable soil, preferably clay. You want to dampen it to improve the compaction of it. You want to be very cautious on putting any type of heavy equipment into that area. You want to do it very slowly, once again, because sometimes there is a bridging effect of that soil of that impacted area of a fire situation. So you want to be really safe and cautious of placing the soil, placing the material in place. You want to make sure you water down the soil to improve the compaction, to once again further seal the area. Then, of course, we talk about the operation of the gas collection system. We'll want to close off all the area, close off the GCCS, make sure it's stable. You want to make sure that you can do that in a safe way. You want to make sure that all your employees are in proper PPE when trying to close off the gas collection system. So, and that's really allowed for in NSPS regulations, that you can close off a well to mitigate a subsurface fire event. You want to avoid excavation, and that's a common theme that people say, well, I'll just go down and dig out all the fire debris, and or try to find the cause of the fire, and that's really the worst thing you can do is go in there and excavate a fire area. Many years ago, when I started in this business, I was involved in a couple fires, and sure enough, they go out there and bring out their excavator and start digging away, and that's worst thing you could do. But the fire just really tripled in size once they started excavating out the material, because once again, you're bringing oxygen into the air and promoting the fire. So the key is, the takeaway here is shut down your gas collection system. It may be multiple acres that you're shutting the system down. You want to and put in any type of compacted soils. You want to mitigate, close off that oxygen, that source of oxygen. Now, once again, that source of oxygen may not be right next to the well. It may be hundreds of feet away from that well. But that's really the part of that effort, is that when you're placing that soil, you want to go around the area and seal off any type of known erosion rail, any type of deep cracks within the cover material. Once again, to mitigate the potential of oxygen coming into the system. Last slide, Craig. Next slide. Okay, and lastly, the obvious question is, well, when can I restart my gas collection system? So it's been a number of weeks, number of days that I have my system closed off. So when can I open the valve back up and return the system to operation? And once again, this is not, there's no standard here. It's not like, hey, 5 days or 24 hours, I can restart my system. It doesn't happen that way, because every fire event is a snowflake. Every landfill is a snowflake. And so it's all really site specific. And you may be able to return it, a few weeks, a few days. It may take many months for you to have the ability to return that collector to operation. In the interim, you want to every so often go up there and burp the well. If it can be safely done, if you can get into the area safely. Once again, I want to stress the word, the safety aspect of all these conversations. That if you can go in there, that the wellhead is still operational, that still has a wellhead valve on it, that you can go there and burp the well. You just want to kind of crack the valve. You hear gas passing by the valve, and then you want to close it off. Once again, the purpose of that is to relieve the internal pressure that's been built up within the waste mass. And that's kind of, once again, relieving the heat, giving the ability for those methanogenesis to return to normal operation and produce methane. So that's the assumption that the casing is still intact. That's the assumption that the wellhead is still intact. You may come up to a situation where the wellhead has been damaged beyond repair, and in those situations, you're looking at just permanently burying the well and re-drilling the well if you have to do that for compliance purposes for your NSPS coverage, or to maintain gas collection in that immediate area. You want to look at carbon monoxide concentrations. You want to develop a profile. And this is where data is really important to really look at your health of your well field. So you want to develop that profile of CO. And once again, you'll need to have that information probably for your submittal to your agency of returning that well to operation. And you want to see that carbon monoxide reading kind of get to what we call normal. Now, normal may be 100 ppm, it may be 200 ppm, maybe 50 ppm. It's really good that for you to develop what you think is baseline. Go to another well that may be on the opposite side of the landfill and get a CO reading, and use that as a point of reference to say, this is what our baseline is. This is what I really want to see my well to be stable at. So that's a good exercise to do to kind of determine what is baseline carbon monoxide concentrations. And lastly, if all that checks out, reestablish vacuum very slowly. Do it in very small increments. really pay attention to your methane concentration along with your wellhead temperature. Now, it's not abnormal to see really a quick spike in wellhead temperature, and once again, because you have all that stagnant gas that's been built up in that collection device. So once that gas is kind of bled off, you can see that wellhead temperature become stabilized, and that's something that you really want to look at. And once again, go back to your old data for that particular collection device and see what is your typical wellhead temperature, typical methane concentration for your devices. And once again, you may have to shut off your well if it becomes unstable, and basically do that process all over again. So with that, once again, this is a high level perspective of really the characteristics between the differences between a subsurface fire and an ETL vent. Really wanted to give you some high level guidance of how to recognize a subsurface fire, how to mitigate one, and then how to restart your system after a fire situation. And with that, I'll turn it back to Brian for questions.
Great, thanks, Bill, and thanks, Mort and Craig, for your presentations as well. You'll see some supplementary reading materials here. I know we're at the top of the hour, but as I mentioned at the beginning, we're going to hit some questions here, and if you're able to stick around, we'd love to have you stick around. We do have quite a few questions. So, Craig, if you don't mind, maybe stop sharing your screen, and we can always pull it
Sure.
up if you need to. So we've had a number of questions come in regarding indicators, and Mort, as Mort mentioned in his presentation, look for multiple indicators, not just one. And so the question that has come in is when we think about landfill fires and ETLFs, and we think about multiple indicators, is there a suite of indicators that directionally point to an ETLF, or I think, Bill, like you mentioned, every landfill is a snowflake. Everything is unique. So how would you make that distinction? And are there certain indicators that you might weight more than others? And so maybe Mort, if you're open to starting that, we can run through that question and see where we land.
I think the simplest one is probably long-term trends in the methane to carbon dioxide ratio, because we do see that ratio seems to decrease, at least at some sites, before the temperature increases. So on the gas side, I'd say methane to CO2 ratio, and obviously wellhead temperatures. And a third might be balanced gas. If you are seeing high balanced gas, the default assumption is it's nitrogen. But if it is nitrogen, that means you're drawing air in. I just don't see that we're making N2 gas in landfills. So if you're seeing high balanced gas, the default assumption is it's nitrogen. But if you can't explain it, in other words, you don't have a broken pipe that's allowing air to suck in, I would do some selected hydrogen analysis and make sure, and you can't do that in the field, you got to do that at a lab. I would do some selected hydrogen analysis. And then the final thing I would do, and this, I don't think we have to do this on every well, but if I had a lot of watered in wells or wells with liquid at the bottom, just check the pH.
Yep.
If it's acidic, it means acids are accumulating, which is probably a biological upset. So, Craig and Bill, I don't know if you want to add to that or.
Well, I just emphasize, I think your point about measuring hydrogen along with carbon monoxide is important, right? As you look at what's in the gas composition, if you're concerned about a fire, see whether you got hydrogen in it. That's a pretty good indicator. If you got 25% hydrogen, it's probably not a fire, right?
Yeah, really quickly, balanced gas, hydrogen will show up in balanced gas of all your handheld instrumentation. And so if in that, let's say, 30% balanced gas, you may want to send that sample off to the lab. And, if it comes back as 5 or 10% hydrogen, then as a reference. Typical, we've seen as high as 20-25% hydrogen in an ETLF situation.
Yeah.
So, anything north of a single digit of, 3 to 4 or 5% hydrogen, we judge that as needing additional investigations.
Yeah.
Okay, great. Yeah, so that's typical in the sense you'd expect to see 50% methane, 50% CO2. You see the hydrogen start to come, you have a biological problem. On the gas side, we start thinking about other volatile organic compounds. And the question that comes in is, what are the differences you would expect in VOC concentrations in gas between a healthy landfill, a landfill that might be smoldering or on fire, and an ETLF? Craig, do you want to take that one?
Well, I can start. Certainly, if we have more VOCs in the leachate, we're going to have them in the gas phase, right? Particularly if we've got an ETLF and not a fire, because they're volatile organic compounds. They will volatilize, right? So we should expect them. I have to admit, though, I haven't looked at that per se, looking at VOC concentrations in landfill gas. So more, Bill, I don't know if you've looked at that in more detail.
Well, I haven't seen a lot of data on that, but just following on what you said, as the temperature increases, chemicals are going to volatilize. So I would expect VOCs to increase in landfill gas as the temperature increases. And then the other source is going to be if we're so hot and there's a pyrolytic reaction, it could be making benzene, for example. But landfill gas, analyzing it for volatiles is pretty expensive and not something we're going to do at every well. The last thing I would say is if you suspect this or suspect an issue, pick 2 or 3 wells in the area you're worried about and 2 or 3 wells in an area you're not worried about and compare them.
Yeah.
Okay, great. So now let's move from gas composition to gas volume. So the question is, I'm a bit confused as to whether ETLFs generate more gas or less gas, as I've heard both. What's your thinking on the issue?
I'm going to start that one.
Go ahead.
I think that this is where it's really important to use words carefully. I think that hot areas of waste are generating less gas. However, often when an operator has an ETLF, not the first thing, but one of the things they try to do quickly is install more gas wells for 2 reasons. A, to minimize fugitive emissions that turn into odors, and to get gas/heat out of the landfill. So I think what we're seeing actually is while the ETLF might be making the same or actually less gas, we're collecting more gas. And that's what we're seeing. Because the temperature is going to shut down the biology. So you're not going to make gas biologically. I haven't seen data on gas yields from pyrolysis. And aluminum corrosion, sure, it makes some gas, but compare the mass of aluminum to the mass of MSW, it's inconceivable that we're getting more gas from an aluminum reaction. So I think they make less. I think we collect more for the reasons stated.
Yeah, I concur completely.
Bill?
I concur also. The only caveat I would say is as a landfill operator, the more gas, more collection devices we install, you really need to be really focused on your available vacuum, your ability to extract that gas. We've had a lot of situations where, we can drill all the wells we want, but if we don't have enough vacuum to pull the gas out of those wells, it's kind of defeating the purpose. And so it's really important that it goes hand in hand, that you are focused on enhancing the number of collection devices, but you really need to make sure that you have adequate blower capacity and also adequate flaring capacity, and you have your proper air permits in place.
Great, thanks, gentlemen. Another gas-related question. Is the inhibition of methane production a result of heat accumulation or a cause of heat generation? Sort of a chicken and egg scenario. The person asking says, we typically focus on heat removal via gas and liquids extraction as a primary solution to manage the issue. So back to the question again, is the inhibition of methane production a result of heat accumulation or a cause of heat generation?
That's Mort's.
Yeah. The inhibition of methane generation is due to the elevated temperature. So something about the site is generating or more heat is accumulating, and that shuts down the methanogenic consortium. It's not the case that there's some unique brand of methanogens that's making more heat.
Mhm. And do you think the heat's the driver first, or is it the low pH that might drive the inhibition?
I think it's probably the heat, because the heat changes the biological process, and when the biological process changes, that's when the acidic decomposition intermediates accumulate and the pH drops.
Okay. Another question that came in, if ETLFs are self-propagating, is there an obvious fuel source that would allow us to predict the extent of such a reaction, or are the fuel sources generally ubiquitous in waste, or is this more of a function of thermodynamics and fuel source is less important?
I'll start that, and then maybe Mort and Bill can jump in. But in general, I don't find we have self-propagating reactions. We have something that generates heat, and as Mort very eloquently talked about, heat moves from hot to cold. It's that simple. It can move by just by thermal diffusion. It can move by convection, where it's moving with another fluid, and then we're getting condensate and we're releasing that heat. But most of what we see of migration of temperatures around a site is due to heat transfer and not due to a propagating reaction. And I think that's something that's really important to think about when we're analyzing a site is, why is the heat moving? And what are the mechanisms driving it? And it could be very likely is just heat transfer. You could have something that's propagating. I don't want to dismiss that entirely, but I find that a lot less likely than just basic thermodynamics. And Morton, Bill, I don't know if you want to chime in there or add to that.
I definitely agree. With Craig's summary there. The one comment I would add is that in order for you to find that movement, you got to make sure that you have devices in the ground to detect that movement. And if that's temperature probes, if that's additional gas collectors drilled at different elevations, whatever the case may be. But sometimes the piece of this puzzle is actually trying to identify where this plume is going, because it's all not going to go in the same direction. You got to have basically some canaries in the coal mine, as they say, to find out where that heat plume is, and to basically give you a head start on creating that boundary to mitigate and to contain that heat plume.
Great.
Just add one more thing on there. Just going back to Mort's comment about the condensate. I remember a site about 15 years ago where I saw this just so clearly. It almost looked like we had heat popping up at locations. And at first we're thinking, what is going on here? But it was just as simple as Mort articulated. It was just we had hot gas loaded with moisture, and then it would get to a cooler region and release that heat. And all of a sudden it would look like we had something popping up. But it wasn't. It was just gas migration and condensation. So we always have to think carefully about what's going on and gather data, draw conclusions consistent with the data and with basic scientific principles.
Thanks, Craig. Most of the guidance for distinguishing landfill fires from ETLFs focuses on landfill gas issues. Any thoughts on something like groundwater data?
Mhm.
Yeah, I'll take a first stab at that one. We have not seen really any impacts to groundwater on the subsurface fire or the ETLF situation. We have not seen any impacts to liner integrity with an ETLF situation that would basically impactful to the groundwater situation. So, really, typically with a subsurface fire, since they are a localized event, shallow event, they're really not going to impact groundwater. So we have not seen any impacts to that.
Bill, that brings me to a follow-on question. You just mentioned the liner systems, and you've not seen any situations, and that was one of the questions. Are there any situations where you all have seen any damage to the liner or anything close to that?
Mort, and I'll kind of Mort and Craig will probably have more comments on this, but if you remember in that slide deck, Mort had that picture of that belly curve. And typically that heat, the hottest part of the landfill is in the middle part of the landfill. And that's what that's what we've seen when we've done similar analysis on temperature profiles. And then Craig had that one picture showing the heat dissipation through the ground, through the substrate. And because of those two situations, I'm not aware of any impacts to liners. I know it is under study, but I'm not familiar with any impacts to it. Craig, did I want to add anything?
Yeah, I'll just add a little bit. I generally concur with what you said, Bill. One of the things I look at is leachate temperatures on the floor. I mean, not from a gas well, but what we're seeing on the floor, because that's indicative of what the gym membrane temperature is going to be. And we do know the anoxidant depletion rates from gym membranes are proportional to temperature. And normally the hot leachate is not on the floor because the belly curve drops down pretty quickly. And we get down to normal ground temperatures. It's usually the hot temperatures are 2/3 of the way down in the waste mass. And so I haven't found damage to any gym membranes. On the other hand, I haven't sampled any at depth. So, but all indications are they seem to be functioning just fine afterwards.
Yeah, we to add in there, we've done some analysis. We have temperature profiles of leachate collection systems at some selected landfills, and we've seen that same profile that Craig just indicated, a coolness of the leachate there. That's really not in is a lot cooler than the hottest zone that's within the waste mass. There's a significant drop off in temperature.
Okay. How do you limit the growth of an ETLF area? Does installing pumps along the perimeter of the ETLF area help?
It's a little harder one. I I would rather focus pumps internal than along a periphery because I want to pull heat out from the middle to try to reduce thermal diffusion away, right? As opposed to putting them on the periphery. I'd be more inclined to put them more internally. Pull the hot liquid out, you're pulling the heat out with it. With that said, I have not analyzed that particular problem. So
Yeah, the challenge there, of course, is really the spacing of those pumps. If you have, let's say, a pump every one per acre, is going to be less impactful than if you have a pump every half acre or quarter acre. And so you really need to really focus on really the scope of that dewatering effort for ET mitigation or containment. You really need to look at the depth of your wells. You need to develop a profile of where your liquid is to begin with, and also really most critical aspect of it, you have to make sure that you got staff enough to keep those pumps
Yeah.
operational, and along with the discharge point. I know in a lot of situations, the discharging of ET related liquids is problematic, and you definitely need to make sure that if you're going to put pumps in, you need to make sure that either you have a storage for the liquid or an offsite location for that liquid, and then the staff to keep those pumps operational.
Bill makes a really good point here. Go ahead, Mort.
Yeah.
I talked already. You go.
No. Two other points. One, I like to point out if I have a swimming pool full of water at 175 degrees and I pump out half of it, the water that's left is still 175 degrees. And so I say that in the context of managing expectations. Another aspect of pumping out water is to help make sure gas wells don't flood or pump water low enough so that they dry out again. So there's more to water than just water. It's part of the functionality of the gas collection system. And all that said, of course, when we pump out water, which we ought to do, we're probably letting gas move more freely, which is good in the context of collection, but probably bad in the context of migration. So I say this just to manage expectations and point out that while pulling out water is important, it's not the magic bullet that's going to make the ETLF cool down.
Yeah.
Well,
I look at, I think dual phase extraction wells are not like a groundwater well where you have a little big drawdown cone and you can create a fence, a thermal fence. They pump relatively slowly and remove liquid from a fairly localized area near the well. It's, I think, more, you talked about that nicely. It's you're removing some of it, but not a lot of it by any given well. Bill, you mentioned too a level of effort to maintain those systems.
Yeah.
Rule of thumb I've been using based on people I've been talking to is one full-time person per 10 wells to keep a system operating. So if you got 50 wells out there, you need 5 people working constantly to keep it running.
Yeah, that's probably a good rule of thumb. One other comment talking about liquids is really the depressurization of that ET zone. Removing those liquids will definitely help to depressurize the zone. Hopefully it'll enhance the removal of the gas. Definitely, once again, when we talk about thermodynamics, it's more beneficial to remove that liquid than gas. It's more efficient, I should say, to remove liquid to address heat, but it's definitely a lot more challenging to remove that liquid. And so, there's there's mechanisms there where we talk about depressurizing the waste mass to optimize the removal of both liquids and gases on a long-term perspective for mitigation of future ET events.
Great. There's this one comment. Craig, you mentioned dual extraction wells. There's a comment about sites that have pneumatic airlines that feed dual extraction or other pumps can be a significant, potentially significant source and risk in the landfill if they're buried or not. Just wanted to see if you all had any perspectives on that. Would you agree with that assessment? And is there a concern with these kinds of pumps?
I would say if you're running air pressure to run pumps, make sure those air pressure lines are carefully installed and carefully protected. Because what I have run into is that they're buried, they get ruptured, and then you're injecting air into the waste and you start a fire. I've seen that several times. I don't know if you've run into that, Bill, at your sites, I imagine.
Yeah, 2-inch pipe is typically your dimension for airline, and that's to me the most difficult pipe to weld because it's done by hand and it's sometimes shaped a little bit, and you got a generally thin pipe wall. But when you over the course of time, those airlines become abandoned or any gas infrastructure abandons because of the additional waste placement. And so it's really important that all those devices are properly abandoned, not just with PVC caps with a lag screw. You want to weld a PE cap onto those onto the distal ends of the pipe, and to mitigate any potential air intrusion coming in. And so, yeah, it's really important that all that pipe is properly buried or properly installed per manufacturer's guidelines, properly supported in the trench, and properly backfilled and installed, per manufacturer specifications.
Okay, great. We'll wrap up with a couple more questions here. Let's stick with water for a minute, maybe sneak back to gas for a moment. Why do we see elevated compounds such as acetone and phenols in the leachate, and what other analytes might exist at high levels to be aware of?
I didn't hear the beginning of that, Brian. I apologize.
Oh,
Could you
why do
repeat
we
that?
see elevated compounds such as acetone and phenols in the leachate? What other analytes might exist at high levels to be aware of?
Yeah. I see the organics as primarily decomposition products. We've got lots of organic matter in the waste that's in a solid phase, and we're decomposing it right under elevated temperatures. And,
Well, and
I
then
haven't
as
done
we
an
get
experiment on
into,
that per se. Yeah,
yeah, as we
go
get
go
into
ahead.
pyrolysis, you're probably making some of those materials.
Agree. Thermal decomposition product from pyrolysis, right?
Yeah.
Okay, and let's see. Back to the comment about gas and whether ETLFs create additional gas or not, no additional gas. If ETLFs don't create additional gas and it's just more collectors, doesn't that imply in-waste accumulation or storage of gas? And a follow-up to that is, could warm liquids generation cause non-reacting waste to degrade faster and therefore release gas faster? And I can repeat those if needed.
Now, I see them in the chat. The first one, if ETLF doesn't create additional gas, it's just more collectors, does not imply waste accumulation. No, to me, it implies reduced fugitive emissions.
Yeah.
At the point where you're putting in more gas wells and not collecting any more gas, it means you're doing the best you can. So to me, it implies reduced fugitive emissions. And then could warm liquids generation stimulate methane generation? Sure, to an extent. If I've got waste at 110
That's cool.
degrees and I get some water on it that's 125 degrees, I'm undoubtedly going to stimulate the rate of methane generation. And that goes to a point. And then when it gets too hot, which too hot is, I forget the numbers. We have a paper on this where we plot, it's in your list. It's the paper where Shoup is the first author. But when we get to between 140 and 149 degrees F, then the rate of methane generation starts decreasing with increased temperature. So absolutely, warm water to a point can stimulate methane generation, and then after a point, it'll inhibit it.
Great.
Depends on how warm the water is.
So
Yeah.
last question, and then we'll end. A bit more of a speculative question in the sense of ETLF mitigation, and I've seen a couple questions come through about cooling ETLF situations down. And there's a question in the chat around, are there any examples of injecting some kind of a cooling agent into an ETLF? There's another question that refers to installation of some sort of a piping or network system where the idea is to cool down the waste mass. Any perspectives on that?
One I'll add, unintended consequences. When cooling systems have been injecting, for example, cryogenic liquids, ancillary effects occur that render the ETLF not the bigger problem. So it can cause more problems than you're trying to solve, I guess. You have to do that really carefully. I like the idea of pulling heat out as opposed to trying to push cold in. That's just my thoughts. Mort, Bill.
I think the volumes we're talking about are just impractical.
Yeah,
The only place I know they tried it, they injected liquid nitrogen and precipitated a slide.
that's what I
So,
saw too, twice.
okay, so that's three examples. Let's not do that. And the quantities are just infeasible.
Yeah.
If we were talking about a real localized area, we can have that discussion, but we're not.
Well, I think that's a really important point too, is that yeah, maybe you want to try to cool with liquid nitrogen. You have to think about how much is it really going to take to do that, right? It's to take it from a concept to a really a practical evaluation of the significance of what we're trying to do. And that's true when we look at all our data too. We want to not just look at it and make a decision. We want to look at it, think about it, interpret it, and then decide a path forward, as opposed to just winging something. Winging things get you in trouble, from my experience.
Always works in the movies, Craig.
Every time I've
Fantastic.
winged things, it doesn't work.
Fantastic. Well, gentlemen, thank you for your time. We got through about half of the questions that are asked. We got about almost 50 questions in. We got about halfway through those. What I'd like to suggest is we try to follow up with answers to those questions and push that out as part of the follow-up materials that we'll send out to the group. I want to thank everybody for attending today. We appreciate you doing so. We do have more science sessions planned for the upcoming year, so please stay tuned. Again, we will be sending out materials that will allow you to see the recording as well as information to allow you to get a certificate of attendance. Thanks again, Bill, Craig, Mort. We appreciate your time and your expertise, and thanks everybody for attending. Have a great day.